Okay, it's Brian here, and we're going to continue our treatment of Chapter 6 by talking about the last topic of the chapter, which is gravity. Now, I want to return to a problem that I raised at the end of the last set of slides, and that's this. Does the reading on a bathroom scale at the equator read more or less than your actual weight? Well, remember, the scale actually doesn't record your weight. It records the normal force. And the question is the normal force greater than your weight, or is the normal force less than your weight if you're standing on a bathroom scale at the equator? And if you're at the equator, you are traveling in a circle, because if you're here, you're on the surface of the Earth is rotating, and so you are going in a circle, and so as a consequence, there's an acceleration directed towards the center of the circle. And so as a consequence, the normal force and the weight force aren't equal. Now, you're actually traveling in a circle at a pretty good speed. Where we live, you're traveling in a circle at about 700 miles per hour. If you're at the equator, you're traveling in a circle at about 1,000 miles per hour. And so you're traveling in a large circle at about 1,000 miles per hour at a very, very high speed. And so we are traveling in a circle. And because that's true, let's think about this. What is the force that keeps us moving in a circle? So if you're here, you're on the surface of the Earth, you're going in a circle, there has to be a force directed towards the center of the circle. And the force is the weight force. And the weight force, of course, is directed straight down towards the center of the Earth. That's how we define down, okay? So think about this. Here you are, moving in a circle, acceleration directed towards the center of the circle. So let's look at the free body diagram of a person in this circumstance. Okay, person standing at the surface of the Earth, there's an upward normal force that is directed perpendicular to the surface and away from the Earth. And there's a downward weight force which is directed towards the center of the Earth. And the question is this: which has a larger magnitude? Now to think about this, remember, there's an acceleration directed towards the center of the Earth. And so as a consequence, there's a net force directed towards the center of the Earth. And since that's true, the weight force has to have a larger magnitude than the normal force. And so the reading on the scale is actually less than your weight force. And it's not a lot. It's not a lot. Let's look at some values. If you are in Mexico City, and your weight is exactly 100 pounds, and in Mexico City, the local value for G is 9.779, because, of course, the value of G is basically related to the weight force. If you have a weight of 100 pounds in Mexico City and you go to Stockholm, Stockholm is further north, it's further from the equator. The local value of G is 9.818. It is bigger. It is bigger. And so as a consequence, your weight is going to be 100.39 pounds. Now, this is not a big deal. That's only a difference of 0.4 pounds, so that's not a huge deal. But a place where it really shows up is if you look at sporting events. And it turns out the first Olympics that was held in Mexico City, because the local value of gravity is basically weaker. People jumped higher. They threw things farther. A lot of records were broken. And it's a consequence of the rotation of the Earth. Now, years ago, there was a time when the Earth rotated much faster. There was a period when the Earth actually rotated once every 3 hours. And if you were back in the period of a 3-hour day and you weighed 78 pounds at the equator, you would weigh 100 pounds at the pole. So then it would have been noticeable. That is kind of a really, really interesting fact about the Earth's history. Now, think about this question right here. Okay, if you're riding in the back of a pickup truck, and the truck turns suddenly, it says riders can be thrown from the truck bed. Why are the riders ejected? Now, it's not like the truck just suddenly decides, out of here, you scamp, we want you out of the truck. What's actually happening is this. If the truck is taking a turn, what's happening is this. The truck is describing the arc of a circle. And if the truck's going in a circle, there has to be a force directed towards the center of the circle. And if you're just riding in the truck bed, the only force that can happen is friction. And so the friction force might not be big enough to make you take the turn. And so what happens is you go in a straight line. So it's not that you're ejected. It's just that the truck takes the turn and you do not. Okay? Now, another place where you have cars going in circles, as we talked about previously, was cars going over rises. And so when a car goes over a rise, there is an acceleration towards the center of the circle. Okay, so as a consequence, the force directed towards the center of the circle, the weight force, is larger than the upward force, which is the normal force of the road surface. Weight is bigger than the normal force. So as a consequence, the normal force between the tires and the road is less than the weight force. And so your apparent weight is less than your weight force, you feel light when you go over the hills. And that's something which we talked about previously. Now we're going to consider this case in class. We're also going to talk about how fast could you do this, like how fast could you drive over this rise before you left the surface. But now we're going to consider this. When you're driving on the surface of the Earth, you are going over a rise, okay, because the Earth is a sphere. And so when you're driving your car on a really, really flat stretch of ground, it's not really flat, it's curved because the Earth is curved. So in principle, if you drove your car fast enough, you would leave the ground, your car would catch air, and you would basically end up in space. What speed would that be? Well, we know. Let's do a free body diagram. If you're in a situation where you're going so fast that your tires leave the road surface, the only force on you is the weight force. And we know if the only force on you is the weight force, your acceleration is equal to g. It's equal to 9.8 meters per second squared. And we know the acceleration in a circular motion is equal to v squared divided by r. And so g is equal to v squared divided by r. V would be equal to the square root of g times r, and in the case of the Earth, you end up with a speed of 7,900 meters per second. So if you could drive your car at 7,900 meters per second, you would leave the surface of the Earth. And in fact, that's what happens with rockets. You just point them in the direction of the Earth's rotation, get them going fast enough, and they will leave the surface of the Earth, and they'll go into orbit, and they won't come back. And the first person to realize this, Isaac Newton, had this thought experiment. He said, suppose I shot a cannonball off a mountain. Okay, I shot a cannonball off a mountain, and I shot it in this direction, and I shot it at a speed such that the acceleration necessary to make it go in a circle whose orbit was just the radius of the Earth, the RE. And if I shot it at exactly that speed, it would just go in a circle whose radius was equal to the radius of the Earth. It would go into orbit. It wouldn't touch down, and it would come back to where it started from. And the acceleration would be equal to v squared over r. The acceleration is g. R is the radius of the Earth, and you could shoot a ball in a circular orbit. He had this idea, and in fact, that's what we do with rockets. You just get them moving fast enough, they leave the surface of the Earth, they go into orbit, and they don't come down. Now, we had an expression previously that looked like this. The speed of an object in orbit was equal to the square root of g times r. And we did a calculation for how fast you would have to be moving to be in orbit about the Earth, basically to have your car catch some air. And we used the local value of g, 9.8 meters per second squared, and the value of r, which would just be the radius of the Earth, and we came up with a speed of 9,800 meters per second squared. But suppose we looked at different objects. Suppose you went to Phobos, which is a moon of Mars. And by the way, Phobos means fear, and the other is Deimos, and that means panic. Mars's moons are fear and panic. Ours is the moon. Come on, people. We got to do better than this. Anyway, suppose you go to Phobos. Phobos's gravity, its surface gravity, is very tiny, 0.006 meters per second squared. And its radius is only 11 kilometers. Okay? And if you put in the values for the radius of Phobos and the value of gravity, you get an orbital speed of 8 meters per second. So something that I would dearly love to do would be to go to Phobos, get on a bicycle, and if you can ride a bicycle at 8 meters per second, which is about 18 miles per hour, and I can ride a bicycle at 18 miles per hour, you would achieve liftoff. You would go into orbit. You would be going so fast you would actually go in an orbit around Phobos and would not come back. And that just sounds amazing. So mountain biking on Phobos is on my bucket list. Now, this is actually a real problem for some smaller bodies if you're trying to explore them, because a while back, the European Space Agency sent this probe called Rosetta, and it was this comet called Philae, and they were trying to land it on the comet, but the gravity of the comet is so small that it was actually hard to make it touch down. They actually had to fire little bolts into the surface of the comet and pull it down because gravity is so weak, and it didn't work, and the thing bounced and it went into orbit, and it was crazy, and it landed in the shade, which is really, really sad because it was solar powered, and so it was kind of a disaster. And the problem is just gravity is so weak. It's actually tough to do something as simple as landing. Now, here's a question for you. What is the force that holds the moon in its orbit? Of course, the force is the gravitational attraction of the Earth. Okay, it's the gravitational attraction of the Earth. A person to realize that was Newton. And Newton apparently had this idea when he was sitting in his garden. And he was looking up at the moon, which is out in the daytime sky. He's sitting out in his garden looking at the moon. And he was looking at the moon, wondering what is the force to keep it in orbit. And meanwhile, an apple fell to Earth. And he said the thought was occasioned by the fall of an apple, that perhaps that weight force, that gravitational force, was the same thing that kept the moon in orbit. Now, it turns out the apple tree on Isaac Newton's estate a number of years ago was getting sickly and looked like it might perish. And so someone took a cutting of it and put it in a botanical garden in London. And someone took a cutting of that tree and brought it to the United States. And someone took a cutting of that tree and gave it to me. And it's living in my garden. And so I actually have a piece of Isaac Newton's apple tree, the very tree which is growing in my garden. And here's an apple that came from it. It's a type of apple known as the flower of Kent. And here's the thing. I don't get very many apples off it because it is prone to early fruit drop. It tends to just drop its apples without warning, and then the squirrels get them instead of me. It's a crazy, crazy thing. And wouldn't it just be prone to early fruit drop? But if you come over to my house at some point, you can say, Brian, where's Newton's apple tree? I'll take you in the backyard, and I'll show you. Now, in order for the moon to have the orbital properties that it does, the force of gravity attracting the Earth to the moon and actually attracting any two objects in the universe to each other has to have this form right here. And this is Newton's law of gravity. The force between any two objects is given by this expression. Mass 1, mass 2, separated by distance r. The force between them, which is always attractive, is big G, which is this constant right here, times the product of the two masses divided by the square of the distance. And this is a law of physics. And I want you to be aware of this because we're going to look at a very similar law that has to do with electric charges in the second semester course. Now, something to note. The m that appears in this equation is the same as the m that appears in this equation. And the fact that that is true is a very, very deep principle of the universe. There's no reason why it has to be true. It is. And this is sort of surprising. And nobody really has a good explanation for it. It's just one of those things that just is. And at some point, we'll discover the deeper principle behind that. Now, why don't you notice this? In principle, you're sitting in class. There should be a force between you and the person sitting next to you. And the reason you don't notice it is because for the force to be big, given that that constant big G is so small, okay, the force is big G times m1 times m2 divided by r squared. Big G is 10 to the negative 11th. It is a tiny, tiny number. So you don't get a big force unless one of the masses is really, really large. The place where we notice it is the force of the Earth on you. And the Earth is really, really big. And so as a consequence, the force of the Earth on you is really, really big. But there's a force between two objects. So if you say, hey, the Earth is attracting me to it, okay? The other way you can think about it is to say, no. There are two forces. They are equal and opposite. I'm going to choose to think about it as the force of me on the Earth. So when I stand on a scale, I'm not measuring my weight force. I am measuring how hard I am pulling the Earth towards me. And if I put on weight, I'm saying like, hey, Earth, I'm tugging a little bit harder. My pull is a little bit more insistent. Now, if you look at gravity on other worlds, okay, it's very, very different, okay? And you can compute a local value for the acceleration of gravity using this expression right here. The local value for acceleration of gravity is just big G, that constant, times the mass of the planet divided by the radius of the planet squared. And you can use that to compute the force of gravity in different places in the solar system. Here's values for the Earth, and if you put in these values, you get a value of 9.8 meters per second squared, as we should. But if you try Saturn, now Saturn is 100 times as massive as Earth, and it's about 10 times the radius of Earth. So think about this, do a ratio problem. If I put in a mass that was bigger by a factor of 100, but I put in a radius that was bigger by a factor of 10, the radius appears in the denominator squared. So I've increased the size of the denominator by a factor of 100. I've increased the size of the numerator by a factor of 100. And so I end up with the value of g, of the acceleration of gravity on the surface of Saturn, that is about the same as the acceleration of gravity on the surface of the Earth, which is... So the acceleration of gravity on the surface of Saturn is about the same as that on Earth. And Saturn is big, but it's also made of very low density material, only about 70% of the density of water, which is kind of amazing. So if you took Saturn and put it in a bathtub, it would float, but it would leave a ring. Anyway, it's kind of a remarkable fact about Saturn. Next piece of the puzzle that we want to do is we want to take the concepts of circular motion that we've been doing and use it as a jumping off point to talk about the subject of torque. And we will do that in the next set of slides.